Hello and welcome to this video presentation on surge protection devices or SPDs. My name is Martin Lavečka and in this video I will talk about types of overvoltages, the impacts of lighting, building protection systems against lighting, electrical installations protection against lighting, and surge protection devices. I'll go through the slides a little quicker and not mention all the details that are written on the slides because this video is quite long. I have tried to make it as easy as possible for you to understand everything in context. However, if necessary, you can pause the video to absorb all the information on the slide and then continue watching. So let's get started. What is overvoltage? We define overvoltage as a voltage pulse or wave that is superimposed on the nominal voltage of the network. It is characterized by the rise time in microseconds, the gradient in kilovolts per microsecond, and the duration. Two types of overvoltage can occur in the network. The first is transient overvoltage. It is a high energy and ultra fast phenomenon that can reach up to 20 times the nominal voltage if it is of atmospheric origin. When lighting falls on overhead lines, for example, or it can reach up to 5 times the nominal voltage if caused by industrial equipment during power supply switching, capacitor bank switching, motor starting, or tripping of protective devices. The second type is power frequency overvoltage, which is the same frequency as the network and can last for several seconds or be permanent. This type of overvoltage can reach up to 1.7 times the nominal voltage and is caused by exposed phase or conductive parts, phase or earth insulation failures on insulated neutral, breakage of neutral conductor, or breakage of a medium voltage cable. What are the consequences of having overvoltage in the network? It disturbs equipment and produces electromagnetic radiation. Additionally, the duration of the overvoltage causes a power spike in electrical circuits that could destroy equipment. Now let's talk about overvoltages in the network due to lighting strikes. The overvoltage can propagate through both the power system and the earthing system. When lighting strikes the overhead power line that powers the building, the surge current and overvoltage can extend several kilometers from the point of impact. When lighting strikes near the power line, the electromagnetic radiation from the lighting current produces a high current and overvoltage in the power supply network. These overvoltages then propagate along the line to electrical equipment inside buildings. When lighting strikes an unprotected building, the lighting current flows toward the earth through the more or less conductive structures of the building with very destructive effects. The building and the facilities inside are generally destroyed. When lighting strikes near a building, the Earth's potential around the point of impact increases dangerously. Lighting generates the same type of overvoltage when lighting strikes near an overhead power line. In addition, the lighting current returns from the earth to the electrical installation. The overvoltage propagates in a common mode that appears between active conductors and the earth, or in a differential mode where the overvoltage appears only between active conductors. Two types of current waves are considered by IEC standards. The first is 10350 and characterizes the current waves produced by a direct lightning strike. And the second is 820, which characterizes the current waves coming from an indirect lightning strike. These current waves are used to define SPDs and equipment immunity test to lightning currents. The maximum value of the current wave characterizes the intensity of the lightning. Overvoltages generated by a lightning strike are characterized by a voltage wave of 1.250 microseconds. This type of voltage wave is used to verify the withstand of equipment to overvoltages of atmospheric origin. Now is the time to discover how to protect a building itself and the electrical installations of buildings from overvoltages caused by lighting. The basic principle for protecting an installation against the risk of lightning strikes is to prevent disturbing energy from reaching sensitive equipment. To achieve this, it is necessary to capture the lightning current and channel it to the earth through the most direct path, make equipotential bonding, and minimize the induced and indirect effects by installing SPDs. Implementing a building protection system helps protect the building from direct lightning strikes. The system consists of the capture device, usually a lightning rod, down conductors designed to conduct the lightning current to the earth, crow's foot, earth cables connected, and an equipotential bond and the earth cables. In any case, the building protection system is not sufficient to protect the electrical installation equipment. 50% of the lightning current discharged by the building protection system returns to the earth network of the electrical installation. The potential elevation of the frames very frequently exceeds the insulation capacity of the conductors of the different networks. Furthermore, the flow of current through the down conductors generates induced overvoltages in the electrical installation. An electrical installation protection system must be implemented to limit overvoltages to acceptable values for the equipment. The electrical installation protection system consists of one or more SPDs depending on the configuration of the building and the equipotential bonding. In today's video presentation, we will focus solely on the surge protection device or SPD. The SPD is a device that limits transient overvoltages of atmospheric origin and diverts the current waves to Earth. To limit the amplitude of this overvoltage to a value that is not dangerous for the electrical installation and the electrical switchgear and control gear. SPD can help avoid irreversible losses or huge financial losses due to equipment damage and service continuity of critical applications. SPDs are the most used and most efficient type of overvoltage protection. They are designed to protect sensitive category 1 and 2 loads and to prevent premature aging of category 3 and 4 loads. SPD eliminates overvoltage in both common mode and differential mode in case the overvoltage exceeds the operating threshold of the SPD it conducts the power to the earth or distributes the power to the other active conductors. As you can see in the image, the SPD is connected in parallel to the power supply circuit of the loads it has to protect. The SPD connected in parallel has a high impedance. Once the transient overvoltage appears in the system, the impedance of the device decreases, so the overvoltage passes through the SPD, bypassing the sensitive equipment. There are three types of SPD. Each one has its specific role in the electrical system. The Type 1 SPD protects electrical installation against direct lighting strikes. It can discharge the back current of lighting propagating from the earth conductor to the network conductors. It is characterized by a 10-350 current waveform that the SPD is capable of discharging at least once. The Type 1 SPD is located on the main LV distribution panel if there is a lighting rod in the building or if the lighting rod is within 50 meters of the building. In another case, we choose SPD Type 2. The SPD Type 2 prevents the propagation of overvoltages in electrical installations and protects loads against indirect lighting strikes. It is characterized by an 820 current waveform that the SPD is capable of discharging once. It can be located on the main panel in case the lighting rod is not present in the building, as we already mentioned in the previous slide, or it is located in the LV sub-distribution panel. Type 3 SPDs have a low discharge capacity, therefore it must be installed as a complement to the Type 2 SPD and near sensitive loads. It is characterized by a combination of voltage waves 1.250 and current waves 820. They are installed in the sub-panel or outside the sub-panel. It should be installed as close to the loads as possible. In this slide, we can see how the energy is distributed between several SPDs, in which the three types of SPDs are provided. SPD Type 1, when the building is equipped with a lighting protection system and is located at the incoming end of the installation, absorbs a very large amount of energy. SPD Type 2 absorbs residual overvoltages. The Type 3 SPDs provides fine protection if necessary for the most sensitive equipment located near the loads. On this slide, we see a real example of SPD protection of a large electrical installation. You can pause the video for a moment if you wish and then continue to the next slide. All SPD types share common characteristics such as maximum continuous operating voltage, voltage protection level, and nominal discharge current. The maximum continuous operating voltage is the AC or DC voltage value above which the SPD activates. The value is chosen based on the nominal voltage and earthing arrangement of the system according to IEC standard. The voltage protection level value is the maximum voltage at the SPD terminals when active. This voltage is reached when the current flowing in the SPD is equal to the nominal discharge current. The value should be chosen below the overvoltage withstand capacity of the loads. In the event of the lighting strike, the voltage between the SPD terminals generally remains less than the voltage protection level. According to the standards, the withstand to electric shock of each device is classified into 4 categories with 4 voltage levels. On this slide, we have an example of the purpose of the voltage protection level. There is a 4 kilovolt overvoltage on the network. Without SPD, the computer would have been damaged because the overvoltage value was greater than its shock withstand value, which is 1.5 kilovolts. But because the electrical installation has SPD protection, the overvoltage was pushed below the shock withstand of the computer. This way, the computer is protected. The nominal discharge current is another common characteristic. It is the maximum value of 820 waveform current that the SPD is capable of discharging a minimum of 19 times. A higher value of nominal discharge current means longer life for the SPD, so it is strongly recommended to choose values higher than the minimum imposed value of 5 kA. Now let's talk about the specific features of each type 1 and 2 SPD. The impulse current is a characteristic of the type 1 SPD and is the maximum value of a 10350 waveform current that the SPD is capable of discharging at least once. The value of the impulse current depends on the risk of financial or irreversible loss in the event of a direct lightning strike. If the risk is low, the impulse current value is equal to 12.5 kA per pole. This value is usually adapted for offices, schools, and residential buildings. If the risk is high, the impulse current value is equal to 25 kA per pole. This value is mandatory for hospitals, museums, public service buildings, and places of worship. Local regulation can define the required impulse current value. The maximum discharge current is a specific characteristic of the type 2 SPD. It is the maximum value of an 820 waveform current that the SPD is capable of discharging once. The value of Imax depends on the level of risk of indirect lightning strikes in relation to the location of the building. Other features for selecting the correct SPD are the number of poles and short circuit current rating. The number of poles depends on the number of phases, earthing management, and overvoltage mode. Normally, the SPD must withstand possible short circuit at the installation point, so the short circuit current rating of the SPD must be greater than the possible short circuit. But in practice, the SPD is associated with a short circuit protection device. The components of the SPD consist of the live part, such as the varistor, gas discharge tube, etc. Internal disconnector, end of life indicator, and external or integrated circuit breaker. There are several technologies available to implement the live part. Each of them has advantages and disadvantages. It is possible to incorporate two leading technological parts in a single device. Some brands incorporate a gas discharge tube between neutral and earth and varistors between phase and neutral. The circuit breakers can meet all functional requirements for installing an overvoltage protective device such as SPD disconnection in case of overload or short circuit, shock withstand, non-Noisian stripping, and continuity of service during SPD replacement. The selection of the appropriate circuit breaker depends on the withstand to lighting current and the withstand to short circuit current. The manufacturer must provide a correct association between SPD and the circuit breaker, because if the circuit breaker is undersized, it may trip unintentionally and cut off the protection of the SPD. In case the circuit breaker is oversized, it may not react when the SPD is short-circuited and can cause damage to the equipment. The circuit breaker may or may not be integrated into the SPD, making it easier to select and install. The end-of-life indication is associated with the internal disconnector and the external short circuit protection device of the SPD to inform the user that the equipment is no longer protected against overvoltages of atmospheric origin. The indication can be local, which is generally a feature required by installation codes, or the indication can be mechanical by disconnecting the integrated circuit breaker, where the position of the control lever allows a natural indication of the end of its useful life. We come to the end of this presentation. You now have solid basics about overvoltage and SPD lighting protection. Thanks so much for watching. Stay tuned for the next video where I will talk in depth about how to install SPD.